Bismillahirrahmanirrahim. I am Alamgir Hussain, Department of Mechanical Engineering, Faculty of Engineering, Islamic University of Medina. Now, I would like to present my presentation on harmonically excited systems. Instructor, Honorable Dr. Fitrani Maduddin, Department of Mechanical Engineering, Faculty of Engineering, Islamic University of Medina. We know in mechanical vibration, harmonically excited system is most important thing. This is the contents: introduction, force vibration, harmonic excitation, equation of motion, transient and steady state solution, solution to a constant force, solution to a harmonic force, response of undamped and damped system, base excitation, rotating unbalance, transient, steady state, and total solution. Self-excited problem and stability, force transmitted to the base, response under harmonic base motion, quality factor and bandwidth, importance of measuring vibration, and last conclusion. Introduction. Force vibration occurs when a system receives external energy through applied force or displacement. If the excitation is harmonic, the system's response is also harmonic. Resonance occurs when the excitation frequency matches the system's natural frequency, leading to large responses that may cause failure. Examples include the machine vibrations, simulate oscillations, and whistle motion on uneven surfaces. The chapter also covers solution methods like transfer function, Laplace transforms, and frequency functions approaches. Force vibration. Before starting explanation, we should know what is the force vibration. According to the books, force vibration occurs when a mechanical or structural system receives external energy during vibration. The excitation can be harmonic, periodic, non-periodic, or random. Non-periodic excitations, depending on their duration, produce a transient response, which is a temporary reaction to a sudden force. In contrast, harmonic and periodic excitation result in a steady state response that continues as long as the excitation persists. Harmonic excitation. A system's response to harmonic excitation is also harmonic, matching the excitation frequency. Examples of harmonically excited vibration include those from unbalanced rotating machines, breeze or tower oscillations due to wind, and whistles of vertical motion on a sinusoidal road. Equation of motion: mx double dot plus cx dot plus kx equal to ft. Since this equation is non-homogeneous, its general solution xt is given by the sum of the homogeneous solution xt and the particular solution xp t. xt, x is t plus xpt. The particular solution will have the same form as the external function and can be calculated following this equation. The homogeneous solution represents the free vibration of the system that dies out with time under each of the three possible conditions of damping, undamping, critical damping, and overdamping, and under all possible initial conditions. There are the condition and the equation. Transient and steady state solution. If damping is present, it can be seen that x is time t dies out and x time t because x free time t after some time. the part of the motion that dies out due to damping. The free vibration part is called transient. The rate at which the transient motion decays depends on the values of the system parameters k, c, and m. To do the analysis of harmonic motion, we ignore the transient motion and drive only the particular solution, which represents the steady state response under harmonic forcing functions. We can see the three figures. It can explain it better. Solution P a constant force. The particular solution will have the same form as the function and be calculated flowing f time 2 equal to f0 m double dot plus c x dot plus kx equal to ft. And there are all the equation how can solve the problem. Solution for harmonic force equation of motion m x double dot plus kx equal to ft. The total solution is x time t xp time t plus x is time t, where x is t is c1. This is a constant cosine omega nt plus constant c2 sine omega nt. XVA cos omega t plus b sine t. The constant C1 and C2 on the homogeneous solution depends on the initial condition and have to be calculated for the whole equation. To find A and B, derive the particular solution and substitute in the equation of motion like this. Before we find the final solution, let's introduce the following concept. R equal frequency ratio Wn magnification factor M, also called the amplification factor or amplitude ratio of like this. See this figure. We can be clear seeing this figure. Here, case 3, R1 equal, the amplitude x becomes infinite. This condition for which the forcing frequency is equal to the natural frequency of the system is called the resonance. Occurs when the forcing frequency is close to, but not exactly equal to, the natural frequency of the system. In this kind of vibration, the amplitude build up and then dimension in a regular pattern. The total solution, this one. Omega minus W equal epsilon when the forcing frequency omega be slightly less epsilon than the natural frequency. The response becomes like this. The frequency of beating is equal to epsilon omega minus Wn. It represents the time when the response magnitude tends in a minimum or maximum. You can see this is the half 2 pi divided by 2 sine omega t. The magnification factor, this one, the critical frequency will be a little bit less than the natural frequency, r critical, root over 1 minus 2 zeta square, r equal on m 1 by 2 zeta, r critical, omega critical divided by omega n, m critical on by 2 zeta root over 1 minus zeta square. Phase angle is 9 for r equal 1, regardless the value of the damping ratio, maximum value of m. And m equal 1 by root over 1 minus r square whole square plus 2 zeta uh, 2r whole square. Characteristic of the magnification factor for an random system zeta equal 0 and m equal to infinity as r equal 1. Any amount of damping zeta greater than 0 reduce the magnification factor m for all values of the forcing frequency. In the degenerate case of a constant force where r equal 0, the value of m equal 1. The reduction in m in the presence of damping is very significant at or near resonance. The amplitude of force vibration becomes smaller with increasing values of the forcing frequency. Example M0 as R the infinity. The maximum value of M occurs when R critical equal to root over 1 minus 2 zeta square. Valid for values of zeta is greater than 0 and less than 1 over root 2. The maximum value of m 1 equal to zeta root over 1 minus zeta square which occurs at r critical. For r equal 1 and m equal 1 by 2 zeta for values zeta is greater than 1 by root over 2. The graph of m the monotonically decreases with increasing value of r. Force transmitted to the base of a viscous system, the steady state response. The spring and the damper transmit force to be base. This is the equation. We can write the sum of cosine and sine in a single cos function with a phase angle ft respect to time t f0 equal 0 root over 2 r square plus 1 and by root over 1 minus r square whole square plus 2r whole square cosine omega t minus phi 1 minus alpha. Q where phi 1 equal tan inverse 1 2 zeta r divided 1 minus r square alpha equal tan inverse 1 2 into zeta r phi equal phi 1 plus alpha equal tan inverse 1 2 zeta r cube divided 1 plus 4 zeta square minus 1 multiply r square. Force transmitted to the base of the viscous damp system. This is the graph and this is the equation that we have seen before. We can go to the next slide. The characteristic of the transmissibility factor TD, the value of TD is unit at R equals 0 and close to unity for small. For an undamped system, zeta equals 0, TD infinity at resonance R equal 1, the value of TD is less than unity TD less than 1 for values of R greater than a root 2 for any amount of damping zeta. The value of PD is unity for all values of zeta at R equal to root 2. For R less than root 2, smaller damping ratio led to a larger value of TD. On the other hand, for R greater than root 2, smaller values of damping ratio lead to smaller value of TD. The transmissibility factor TD attains a maximum for zeta greater than 0 and less than 1 at the frequency ratio R equal Rm given. Rm equal 1 by 2 zeta and root over 1 plus 8 zeta square minus 1 whole square. Response of a damped system under the harmonic motion of the base. This is the ratio of the amplitude and the graph. How can we find TD equal xp equal y0 and TD equal that we seen before. Force transmitted to the moving base of a viscous damped system. The equation 1 by root over 1 minus 2 zeta square which occurs at critical for values zeta greater than 1 over root 2, the graph of r square m does not attain a maximum. Its value grows from 0 to 1 when r, the transmission force. Force transmitted viscous dampness system under rotating unbalance. This is the graph and this is the equation. And all graphs for this system, all the equation. This is the system. And quality factor Q and bandwidth F t equal f0 cos omega t. The value of the amplitude ratio at resonance R equal 1 is also called the Q factor or quality factor. For small values of damping, zeta is less than 0.05, we can take R critical equal to 1. This is the equation. Quality factor Q and bandwidth, the points R1 and R2 called the half power points are set where the amplification factor falls to Q divided root 2. This is because the power absorbed uh, del W equal pi c omega x square by the damper responding harmonically at a given frequency is proportionally to the square of the amplitude. They can be approximated. R1 square equal 1 minus 2 zeta, R2 square 1 plus 2 zeta. The difference between the frequencies associated with the half power points R1 and R2 is called the bandwidth, and del omega and can be calculated del omega omega 2 minus omega 1 equal to 2 zeta omega n. The quality factor Q can be used for estimating the equivalent viscous damping in a mechanical system. Can also be calculated using the following expression: Q equal 1 divided 2 zeta equal omega n omega 2 minus 1. Importance of measuring vibration. Measurement of the vibration ensures adequate safety margin. Selecting the operational speed of nearby machinery to avoid resonant conditions. Mechanical models may not represent actual value due to assumption. Information about ground vibration due to earthquakes, fluctuating wind velocities on structures, random variation of ocean waves, and road surfaces roughness are important in the design of structure, machines, oil platform, and whistles suspension systems. Conclusion. In conclusion, harmonically excited systems exhibit critical behavior such as resonance and damping effects. Understanding transient and steady-state responses, magnification factor, and force transmissibility is essential for designing safe and efficient mechanical systems. These principles help prevent excessive vibration and ensure optimal performance in various engineering applications. Thank you so much.